Welcome everyone to the MFEM tutorial. This is part of the Livermore's HPC software tutorial series in collaboration with Amazon Web Services. It shows you how to use MFEM in the cloud. MFEM is a C++ library for finite element methods that we're developing at Livermore in the Center for Applied Scientific Computing. But it's really an open source project with a lot of folks in the community helping from all over the world, and you guys are part of that. We really appreciate this opportunity to tell you more about it. Maybe some of you are already developers or will become developers. We're an open and welcoming community. So for this tutorial, we have 2 hours today, and it's basically a self-paced set of pages that you can go through and learn the basics of MFEM. This is not an advanced tutorial. If you're interested in more advanced, cutting-edge MFEM features, we have a workshop, a community workshop that we run every year in October. And this year's is October 22nd to 24th. So I will encourage you to sign up for that. And that is hybrid. It could be in person or virtual. What we're going to do today is go through a set of lessons. We have 6 of them. They're here. Getting started, basics, and then you have a choices of how to proceed, and then we wrap up with further steps. And these are lessons that you will be able, of course, to do today, but you can also do on your own. We have a version of the containers that we use for these lessons, these Docker containers that you can just download, run on your own machine, or deploy them in your own cloud if you want. There's some instructions for that. Today, we provide a AWS instance for you where you will be able to follow these lessons and learn about it's an introduction basically to the MFEM's capabilities, what it can do, and hopefully how it could be useful for you. Okay, I will be doing some of these demos just to have things going in the webinar, but really it's up to you. It's a self-paced tutorial. You can follow with us, or you can do it at your own pace. You don't need to do everything. You can focus only on the things that are interesting for you. We have the Slack today where you can ask questions. Please use that as opposed to WebEx because it could be more interactive and it's saved. And of course, you can just unmute and ask questions on WebEx. Okay, so let me pause here for a second and ask you if there's any questions so far. Okay. Now, the first thing we're going to do is the getting started page. And each page, each lesson has an estimate of how long it will take and what's the level. This is something that we all have to do to get going. And it should take about 15 minutes. The goal is to set up a browser-based environment for MFEM development. You will see what it looks like. It's an editor and a terminal and a visualization tool. And just run a simple MFEM example to test that environment, make sure it works. What you need to get started is an IP. This is the IP address of the AWS instance. And as part of this tutorial, you should have gotten an email with a Google form where you put your address to request such an instance. If you have not done that yet, I will now post a link in both the WebEx. There are some instructions already on Slack, but I will also post this in the WebEx chat. Okay, here we go. Okay, there is a Google form to request this instance. Once you requested the instance, you should have gotten then another email with the actual IP. And that's what we're going to use in the rest of this page. Where you see IP, that's the IP address that you've been assigned. Everybody gets their own machine, and you will be able to run in parallel using multiple cores and so on. If you are using VPN, we would recommend turning that off. Sometimes we've had issues with it. If you are inside the lab environment, you may use something like SafeWeb, because we are going to point to certain ports, and sometimes these ports are blocked. Okay. Any questions so far? Okay, so let me just do these first steps. You can, of course, do them by yourself. You don't need to follow me here. First, you open a new browser window. This will be your terminal and your editor. And you take your IP address at port 3000. For me, and please don't, I will put my IP address on the screen. Please do not copy mine. As I said, this will mess things up. Everybody gets their own. So this is the one that I got, and for 3000, you will get this. This is basically a Visual Studio in Visual Studio Code in the browser. Click here on Mark Done. Okay, so we're just following basically what's on the page. You should see something like that. It's the same with this image. Open folder, MFEM. Okay. Okay. Then open a new terminal. You can do this in various ways. You can do it through the terminal window here. You can also press Control Shift check mark, I guess. I'm not sure what this key is. All right. And you can also, you can go here in examples, for example, and open, I think, what did we say? Example 1. All right. Okay, so this is just a regular Visual Studio Code. Maybe you're already familiar with that. On the left, you have the MFEM source. Here is one of the examples, and this is a terminal. And you can see here, for example, with the top of the MFEM source directory. Okay, you can adjust things, of course. This is a fully functional Visual Studio. Okay, so this is the editor. Any questions so far? Is everybody able to do that? Any trouble up to this point? Okay, I'm not hearing anything, so I will assume we are doing okay. 3000 is not a standard port for AWS. This is particular to this demo. Okay, now we're going to open a second window. So open another browser window. I'll make it a little bit smaller and kind of put it to the right here. This is where we're going to do we're going to see our visualization. So we are going to be computing and editing on the left, and then seeing the results on the right. All right, and I'm going to move this here. This is the same IP address, but the port is 8000, and we're in a page called live. So colon 8000/live, and you should see a window that looks like this. Okay. Right now you have these two codes. So this is the Visual Studio instance, and this is our visualization code called GLVis instance, running on different ports on the AWS nodes you got. They're not connected right now. And so we will connect them. So whatever we do here shows up here. The way to do that is to move your mouse to see those icons and click on this one that says connect to socket. It's in the upper left corner. Click on connect. Once you see disconnect here, just click outside of it. Okay, these are the instructions here. And it says your environment should look like this. And it does. Okay. Okay, any questions up to this point? Is everybody able to get to this setup? All right, now just to make sure this all works, in the terminal here, get inside the examples directory, see the examples, and run example 1. So this demo comes with pre-built serial and parallel versions of example 1. The current directory is not in the path by default, so you need to say /example1. And I will minimize this so you can observe what happens in the window once I run it. So you saw 111 iterations. You can kind of go through, you can scroll to see the output of the example, a mesh and order and parameter that we used to this for this simulation. It's a simple Laplace problem. It's a preconditioned conjugate gradient iterations converged after 111, and the mesh updated to this, and you can use the mouse to move it a little bit. Okay, once you get to this point, you have a functional environment, and we can proceed with the rest of the lessons. So I will pause now to answer questions and make sure everybody's we're on the same page here. Again, please ask questions in Slack, preferably just so we can answer people individually. And if you're not on Slack, there's a link that we sent you earlier in the email to join. And otherwise, of course, you can also ask on WebEx. And please feel free to unmute if you have trouble and ask. The question is if the port in the socket connection should be 3000. No, the port should be 8080 as it is by default. There is, I can explain why, but there is basically another socket there's another connection between these two windows that happens on this port. So don't change what's there. The editor is at port 3000, the visualization is at port 8000, and this is 8080, and it should be just left the default value. Okay, any other questions? Okay. At the end of each lesson, you have, of course, a reminder to ask questions on the channel, but you have next steps, and sometimes you have multiple choices. In this case, the thing we want to do next is go to the finite element basics page, and of course, you can just go back to the tutorial where you have all the pages, and you can pick from them. When you're deciding what to do, take a look at the short descriptions here of what each page includes. After the finite element basics, that kind of introduces what finite elements are, how MFEM discretizes them, gives you a wall, an annotated version of example one, how to do serial and parallel, how to use some of the visualization keys in GLVis. After that, you can look at examples. We have a lot of them. You can look at meshing and visualization, or solvers and scalability. Each of those are independent lessons, and you can do them in any order you want. And then at the end, we have quite a few additional things you can do if you have time, or if you want to do it after the tutorial. Okay, so I am going to go now in the finite element basics page and go through some of it. But please, again, you don't need to follow this. If you have, you can go at your own pace and maybe go faster or slower. If you have questions, please ask on Slack, or feel free to interrupt me and ask questions here on WebEx. Okay, so this lesson, I don't know if it will take 45 minutes, but maybe if you do it slowly, it will take 45 minutes. The goal here is to understand a basic discretization of a simplest partial differential equation, the Poisson equation with MFEM, and show how to run some serial and parallel runs and how to visualize the solution and manipulate this visualization that we have in this window. Okay, so this is going to be really basic. If you know finite elements, you can, of course, skip that. If you don't know finite elements, I'm not sure you will learn it from this. We have other resources to give you more detailed introduction. But this just to kind of get you on the same page and at least give you some of the basic concepts, so you can understand what's happening in the examples. That's the goal here. All right, so the first example in MFEM solves this equation. This is the Laplace operator, so the sum of the second order derivative of u equals f. This is a very standard equation in computational physics that models all sorts of things, membranes, heat distribution in the static case, when things have been equilibrated over time. To discretize this, to represent it on a computer, we represent and approximate the solution as a sum of a linear combination of finite element basis functions. So to do that, we first take the geometry. This equation is posed over some continuous domain, and we discretize this geometry with little elements. These are the finite elements, in this case, little quadrilaterals. The more we have of them, the higher the resolution, the higher the accuracy. And at each vertex or edge or face of this mesh, this collection of elements, we have a basis function. For the Poisson problem, the natural space is a continuous space called H1, and the basis functions look like this in the lowest order case. You have 1 at a vertex and 0 everywhere else, and outside of this immediate vicinity of the vertex, the basis function is 0. Okay. So we have little hat functions like that. Those are the phi j's. And we take a linear combination, and that's our approximation UH to the exact solution U. And that's what finite elements are. The finite sum of elements. Now, of course, this is very, very simple. Things can get much more complicated. We can have meshes, for example, that are curved, that have adaptive mesh refinement that look like this. We can have more complicated functions, in particular high order functions. We can have more complicated spaces that are not just degrees of freedom at vertices. And MFEM supports all of that. But for example one, we're going to focus on this simple case. Now, this is a continuous level equation. And so to make it to make it something that we can represent on the computer, we plug in this approximation UH, which is the sum of coefficients times the basis functions. And that's basically this thing right here, these two terms. And we test, which means we multiply by a basis function and we integrate over the computational domain. So we test with each basis function. This is called the weak form. And the reason this is done with finite elements, there are many theoretical reasons for this, but one of them is it allows us to reduce the smoothness requirement on our basis function and on the solution here. Because once we do that, we immediately integrate by parts using the divergence theorem. And this assumes here that we have zero boundary conditions. So the boundary term that you will get from the divergence theorem goes away. And you get this thing here. And this is called the weak or the variational form of the Poisson problem. And that's what we actually solve. It's not the equation in this so-called strong form. It's the equation in this weak form where we have tested against some test functions and integrated by parts. What's nice about this is that you can write it as a system of linear equations. A is the matrix that corresponds to this term here. It's just the integral of the inner product of the gradient of the basis functions. It's called the stiffness matrix. B is called the load vector, and it's an integral of the right-hand side of the partial differential equation times the basis functions. And these coefficients in front of the basis functions, it's our vector of unknowns. And these unknowns are called degrees of freedom. And so AX equals B is a global linear system over all degrees of freedom. In this case, each degree of freedom corresponds to a vertex of this mesh, so over all vertices. That corresponds to UH, an approximation of U, and as we take finer and finer meshes, we get better and better approximations. Okay, I'm going to stop here, and I hope this was somewhat useful to some of you. There's much, much more to learn about finite elements. There's a lot of advanced functional analysis theory. We have a page on the MFEM website where we list some of our favorite textbooks on the subject. We also have a variety of additional pages that explain in more detail the different weak formulation we support. They're called bilinear forms. I'm just going to show some of them. As you can see, they're all kind of inner products of some derivatives. This U and V are the solution and the test space, and you can have things like cross products and curls and more interested vector functions. And we have this other page here which says weak formulations, where we go into a little bit maybe more detail of how you can take a strong form of an equation and derive its weak form. Okay, so I'm gonna come back here and just focus on the main things. To discretize PDE, we need a weak form. We call this bilinear form in MFEM. We need a right-hand side. We call this a linear form. And we need unknowns. We call this a grid function on a mesh. Okay, so how does this look in code? MFEM example 1 solves this exact problem. So you can, of course, click here and look at the documentation on GitHub, or the source on GitHub, or you can just look at it in your Visual Studio Code window here on the left. All right, so the first thing you will see here is the definition of the mesh. Okay, that is again the beginning object. That's the discretization, the computer representation of the geometry. And for us, in this example, we read the mesh from a file. And the other thing here that happens is you take the dimension of the mesh. So is this a 2-dimensional mesh or a 3-dimensional mesh? If you look at the example that you run here, the mesh was actually specified by default to be this star mesh in the MFEM data directory. Okay, so you take the mesh, and then you can refine it. Refine it means you take the element and you split it in smaller elements. For example, you take a quadrilateral and you split it in 4 quadrilaterals, put the midpoint lines. The way this refinement loop here, this is, you can do this uniformly or adaptively, locally. This is uniform refinement here. And this here is just a fancy way to get about 50,000 elements in that mesh. You can prescribe the level of refinement yourself. You can change this number 50,000 to other numbers if you want. Okay, so we start with the mesh. Then we create the finite element space. So this is the space of the basis functions. And I mentioned that continuous finite elements are known as H1. So we define a finite element collection, which is a H1 collection. Here's where we use this dimension of the mesh. So this could be a volume mesh in 3D, a mesh in 2D, or surface mesh in a 2-dimensional surface mesh in 3 dimension. And MFEM is a high-order code that allows much more than just the first-order basis functions that I showed. Here's where you specify the order: first, second, third. In general, MFEM supports arbitrary order, but you want to use advanced partially assembled methods if you go to higher orders. Otherwise, this matrix A becomes very dense. Okay, so taking this finite element space with the mesh defines an object. This finite element collection with the mesh defines an object called finite element space. And this is where our grid functions live. This is where our approximation UH to U is. And here what we do is we output what's the size of that space. In this case here, for the example we ran, that was about 20,000 unknowns. Okay. You notice, for example, here, and I will start pressing some buttons here, but bear with me, I will explain what those are. Everything on the boundary here is 0. Okay. And also, just so you see, this is the computational mesh that we used in this example. Okay. To enforce these 0 boundary conditions, it's called Dirichlet or essential boundary conditions. We extract them with this get essential true-offs method of the finite element space and store them in an array. And later we use them we use this list to eliminate them. Okay, so we have the mesh, we have the space. The right-hand side, as I said, is what we call a linear form. This constant coefficient 1 as an argument of a domain linear form integrator means that f, the right-hand side here, is the function 1. Okay, and linear form, domain linear form integrator means integral of this type, a function times a basis function. As I said, we support a wide variety of different types of linear and bilinear forms with different kinds of derivatives and assumptions on the spaces, the smoothness of and the continuity of the spaces. Okay, you can change this constant coefficient to a general function, and then you will be integrating f, whatever that function is, times the basis functions in this finite element space. Okay, and when we say be assembled, that produces a vector. Our known that was denoted before with UH, here is denoted with X, is a grid function in the space. We initialize it to be 0. The matrix is a bilinear form. We can support different assembly level of this bilinear form, which means we can produce really a global matrix as we did here, or we can produce a decomposed form of this matrix that is much better for high performance computing and GPUs and higher order methods. These partial and full assembly levels. PA and FA are actual options, command line options that you can specify. By default here, this is full assembly, so this computes a matrix. And the integrator, this diffusion integrator, corresponds to bilinear form like this. This form can also have a coefficient in front that is set to be 1. So it's exactly this thing. Otherwise, more generally, this equation looks like minus divergence of a coefficient times the gradient of u. In this case, the coefficient is 1. So it's really just the Laplacian. Okay. And then we assemble it, which means we produce a matrix. Okay. Now, we haven't quite produced the matrix yet. Based on these finite element objects, the list of essential degrees of freedom, the grid function, and particularly with its boundary conditions on these essential degrees of freedom, which remember 0, the linear form and the bilinear form, we have this method called form linear system that takes those finite element objects and translates them into linear algebra objects, a matrix A, a vector X, and a right-hand side vector B. Okay, and of course, in this problem, we output the size. It's the same. The size of this linear system is the same. And then we solve this with the preconditioned conjugate gradient method. This is a SPD matrix, so this is an appropriate iterative Krylov method for solving this. And this is for example, this means that the tolerance is 10 to the minus 12. And we use a simple preconditioner, very simple one, which is a Gauss-Seidel smoother in this serial case. Okay, this typically is one of the main bottlenecks in a finite element computation. Okay, after we've solved it, we can then go back from linear algebra to finite elements with recover FEM solutions. And now X contains a grid function, the approximation to the continuous solution. We can save this to disk, and we can save it with sockets to GLVis, our visualization, and that's what happens by default, and that's why this window updated. Okay, so this is an overview of this example 1, the serial version of this code. It's a bit abbreviated, but as you can see, it's about 200 and less than 300 lines of code. And this is a general code that can run all these sample runs and much more with different meshes, different orders, different partial assembly, and other options. Let me pause here and ask if there are any questions on this one. I know there are questions on Slack, and some of them from developers that are here are answering them. Anything that we should discuss on the WebEx, please unmute and ask if you want to. Okay, I see a question about the mesh generators. We will discuss this, but generally, MFEM is not a mesh generator. We can import pretty much any mesh generator that you can think of, probably, and if we don't support it, it's easy to add input. Assembly, I think I answered this question. Assemble, depending on the level of assembly, either assembles a global matrix, local matrices, or assembles what we call partial assembly, only data at quadrature points. Okay, so this is example 1, the serial version. It's relatively straightforward. very easy to build. If you build the serial version of MFEM, it has no dependencies. It's quick to download and build, probably take you 10 minutes to run this. And you can use it kind of to do research, to explore things. One of the nice things about MFEM is that then you can take this and turn it into a very performant HPC version of that example. We call that example 1P. It's this file here next to it. These two are designed to be diffable, so you should be able to see the differences, and the differences are small. That's the point. You can develop in serial, and then when you decide you're ready, you can make a few changes, and now all of a sudden you're running in parallel in a scalable way. You can use the supercomputers. So what are the differences? Well, you need to initialize MPI, and in parallel, we also depend on Hyper. That's the one dependencies that MFEM has. We could also use PETSI as an alternative, but we need some sort of parallel sparse linear algebra library. The other difference is that in addition, you still have this serial mesh portion, but in addition to that, we have another portion for the parallel mesh. And what that means is at some point after you've refined in serial, you split the mesh based on your MPI ranks, and then each MPI rank gets its own independent portion of the mesh. Now these are smaller pieces, and to increase the resolution, you can refine those pieces in parallel independently of each other, and that's what we do. We add 2 more refinements in parallel on each of the MPI ranks. And all of this is configurable, of course. So there's this, now we have a parallel in addition to the serial mesh. That's one new thing. The other thing is mostly cosmetic, and that's that all these spaces, all these objects, finite element space, linear form, grid function, bilinear form, they get a par prefix. They have parallel versions that are basically the serial versions plus something else. Maybe something that has to do with now degrees of freedom could be shared. So you may have multiple copies of the same vertex on different MPI ranks, for example, and need to negotiate that. But this happens behind the scenes, and from a user perspective, you just add the par prefix to several of the classes. And for example, you have par finite element space here, par linear form, but the rest, the only difference in this block of code, for example, is that there's par here. Okay, now the main difference is the preconditioner. You cannot use Gauss-Seidel anymore if you're running in parallel and at large scale. So you need a much more powerful preconditioner. And MFEM is very tightly coupled with Hyper. That's one of the reasons we rely on Hyper for sparse linear algebra, because for us, we directly assemble in Hyper matrix format, and there is no conversion needed to access Hyper solvers. Hyper, if you're not familiar with that, is a library for scalable linear solvers, particularly parallel algebraic multigrid that's also developed at Livermore. Okay. So a preconditioner to use Hyper's algebraic multigrid, Boomer AMG, to define that precondition, it's one line in MFEM. We have this slightly different interface to PCG, but it's kind of object-based, but it's the same. It's more explicit in terms of the tolerances you said. But the really one relevant line is this set preconditioner, and as you can see, it's just set preconditioner, basically Hyper Boomer AMG. And then you set the operator, and solving XB is kind of like multiplying with the CG object. It's like A inverse B equals X. Okay, and that's it. That's kind of the changes you need to go from serial to parallel. We have a whole lesson where we go in more details on solvers and preconditioners and how to get scalable performance. All right, so this completes kind of the teaching portion of this. Now we're gonna do some runs. And we're gonna run example 1 and example 1p and see what happens. So let me, you can try those yourself. Maybe you already did. Oops, I pasted in the wrong place. You can in general copy and paste here, and I will have this open. This shows that you can use the example with just changing different meshes. And this, for example, is a 3-dimensional mesh. And it's the same code. You can see the solution inside. I'll put also color bar here. So that's called Escher. It's a tetrahedral mesh. This is a 2-dimensional problem with non-reentrant corner. The MATLAB logo has this, the eigenfunctions of this. You might be familiar. And then I mentioned we also can do surfaces. So this is a surface example. It takes a while when you run. It may take a while for the visualization window to get updated, because what happens is this happens instantaneously in the cloud, but our visualization runs inside the browser with JavaScript, and so you have to get from the cloud locally the data. Once you get it locally, though, the interaction should be instantaneous or very quick. Okay. I did mention that in the beginning of the example, we have a bunch of sample runs, and you can try all of them. You can say example 1-h, and it will show you the different parameters that you can provide on command line, and you can look at the data directory and see some meshes that we that come prepackaged with MFEM, but of course you can get others. So this right. So this is some example 1 runs, and as I said, you may need to wait a little bit for the visualization window to update. Let's try some parallel runs. Example 1p. We need MPI run for that, and NP is the number of processes we use. Oh, so you run this and it doesn't work. That's because we don't have really 16 cores on this particular instances that we've been able to reserve. So you can get around this by using the oversubscribe option. You can either use less cores, and I'm not sure what, maybe we can do 8. Yeah, okay, so 8 works. Without oversubscribe, so you can either reduce this number, or you can use oversubscribe to force using more cores. It's not going to be high performance, but it will run. And notice some differences right away. We have much less iterations. Okay, before it was in the hundreds, now it's 23. And you know, we're actually solving even bigger problems here. It's about 80,000 degrees of freedom. You can of course adjust that. And what happens here, and I will show in a moment how to do that, is you're solving on independent pieces of the mesh. And these are the 16 independent ranks. I'm gonna make this big, so maybe you can see better. And this is kind of the solution that this is the parallel mesh that I mentioned. These are the pieces of the serial mesh that have been split and then refined independently. And through the parallel objects, these local computations are synchronized in a way to compute a global solution. Oh, F12 is overwritten here. To compute a global solution that is continuous and in this space H1 where the actual solution is. Okay. Okay, and there's some instructions here to do how to do some of that. Let me try to be ambitious here and see if we can do 48. maybe I'll regret this. We need to put oversubscribe. So this is the 48 parallel MPI ranks on a curved version of the Escher mesh. Escher P2 means second order geometry. Remember, the Escher mesh is TEDs. Okay. And these are the 48 pieces that you see where we've done individual computations and then stitch them together. All right, there is a section here on GPU runs. MFEM is GPU accelerated. It has been for quite a few years, actually, more than 5 years in our official releases. That was a major effort in the MFEM project during the last 7 years, I would say. We have GPU-enabled supercomputers and GPU-based supercomputers at Livermore, so this is very important for our applications. These instances that we have today do not have GPUs, so you cannot try those today. But if you do have a machine with a GPU and you run this tutorial, if you just download and use MFEM, you can provide a device with the -D option and run example 1, for example, on CUDA, and then you can also use different solvers like NGX, which is AMG version specific for NVIDIA hardware. There's another directory. There's set of directories, by the way, under examples that have specific versions that show things like SuperELU, Sundials, AMGX. And these are the instructions how to do that. I'm not going to go today a lot in GPU computing beyond this, but almost a vast majority of MFEM examples have this option -D. And the difference to use devices and GPU acceleration in MFEM is, at least at this high user level, has really been just adding these lines here to specify device configuration that can support a lot of different options. And then everything under that, including memory management, kernels, and execution of these kernels, happens at a lower level that high-level users of the library don't need to worry about. All right, this did take 45 minutes. That's interesting. The end of this lesson is about the GLVis interface, and you will see a number of keys here that are kind of the magic keys that you can use to quickly adjust things. So, for example, this pulling apart and bringing it back together parallel domains is F11 and F12. So F11 just works for me, but on a Mac, F12, at least in Chrome, does this. So on a Mac, you need to do Command F12 if you want to press F12. So this is F11, F12. M opens and M shows the mesh and level lines or nothing. That's it circles between those. A is anti-alias in capital A. It's I don't know if you can see the difference. Maybe locally you can. It's a little bit better quality. Lowercase a is the axis, and there's several different forms, so you see where you are. C is the color bar. G is background, black or white. One useful thing for 3D, and let me bring it back and remove some of these things, make it bigger. One useful thing in 3D is a cutting plane, and I showed this earlier. That's I, and I has several modes, either a straight cutting plane or the elements behind the cutting plane or nothing. And once you have the cutting plane, you can use X and capital X the other direction, Y and capital Y, and Z and capital Z to adjust the cutting plane. Okay, P changes different color palettes, which we have quite a bit here. And you can go back with capital P. R kind of resets the point of view. And then you have this capital R, which is the 6 2D projections. Left mouse button turns, right mouse button zooms. Yeah, I think this is these are most of the things. This web interface also has a bunch of controls. Kind of some of these things made a little bit more user friendly. If you click this gears button here, for example, turning on and off the mesh from here, or the elements from here, or showing the axis, switching the color map, light on or off, material, color bar, background, and some of the things that I showed. If you prefer the keys, there is a help here with this question mark on the left. That kind of should explain all the keys that you can press. Okay, I'm gonna pause here for a while because I think this was a lot of material. We covered quite a bit, but this should give you at least the foundation of what's going on in a simple example, how to run it, maybe how to change things, and hopefully how to use the visualization. Oh, so is it not possible for WebEx attendees to unmute and ask questions, Christy? I thought that they can. This is the first we've done this webinar, so it's a bit new for us. If you cannot unmute, please ask questions. Please use the chat and Slack. Okay, I see a lot of questions and I see a lot of answers. Anything I can provide more information about or repeat, explain better? I see. So maybe you cannot unmute. That's I didn't realize that. So then just use the chat. Yeah, any resources for to work to develop the custom bilinear integrators. But that is a excellent question. That is, I would say, a bit advanced topic. We do have, first of all, we have a lot of bilinear and linear integrators. And the first thing I would say is go through this page and make sure that it's not there already. Very likely it is, unless you're doing something non-standard or you're doing some research in some new types of finite elements and forms. But we do have a lot of those. We have continuous H1, HCRL, HDiv, discontinuous Galerking, we have DPG, we have isogeometric analysis with NURBS. So we have quite a bit. There are some of the pages here are intended to help you define your integrators. It is not as simple as just providing UFL in MFEM, particularly because we are trying for these integrators to be very high performance, so the kernels are independently written usually. But I would say, you know, there's this page here that's that will linked, and that does help to some extent. But we of course also always open to assist you, and you can look at some of the previous integrators. Oh, I can unmute things. People, I didn't know I can. I see. Okay, I guess folks, if you want to speak up, you could let us know, and we can unmute you to speak. But I'll try to do this on my other screen. Okay, any other questions? Okay. From here, we can go to any of these 3 pages here, and they all, I think they all take a while. And I can try to cover them, but I will have to speed up. Do people have a preference between examples, meshing and visualization, and solvers? I'll wait for a second. All right, let's start with examples. Okay, this tutorial is hosted on the MFEM website. So if you click on this, the MFEM here, this is the main MFEM website, and some of the features that I mentioned are there. But in particular, if you go to examples, you will see a large gallery that you can filter by of example codes. There are many of them, and we have at this point almost 40. Actually, we do have exactly 40. And then we have versions of these examples, for example, IGA, NURBS versions, and then we have a bunch of mini apps. So there is a lot that you can start from to build your application. These examples are intended to be not just for teaching, but also as main building blocks. So I'm going to go through some of these examples in this lesson. They have to do with the general DRAM complex. So this is the H1, H-curl, H-diff, and L2 finite element spaces, nodal Lagrange finite elements, Nedelec finite elements, Rabiat-Tuma finite elements, and kind of discontinuous finite elements of different orders. And this diagram shows these 4 spaces where the degrees of freedom are in the lowest order at vertices, edges, faces, and the interior of the element. Also at higher orders, what happens when you increase the polynomial order. So for example, here you get this Gauss-Lobato quadrature on each of the edges, and then a tensor product. For Nedelec, it's more complicated. It's some dot products with some vectors in particular points, similar for Rabiat-Tuma. And for L2, it's typically values at some quadrature, for example, that's Laplace-Legendre. Okay, so in MFEM, you have example 1 basically for this space. Example 2 is a vector version of this space. Example 3 is this space. Example 4 is this space. So the first 4 examples kind of give you a flavor of all of them. Now, one thing is, I mentioned earlier that only example 1 is built. So if you try to run example 2 right now, it will tell you that there is no such example because it hasn't been built. And so let's build that example, and I will actually build all 4 of them here. You just say make and the example names, so 2, 3, 4. And you can similarly build the parallel versions of that, just the same each serial example. Most of the serial examples have an accompanying parallel ones. So example 2p, 3p, 4p. All right. Okay, so we already discussed example 1. That solves the Poisson problem with H1 elements. And this is some additional sample runs for this. So I'm gonna skip this one. Example 2 is linear elasticity. And just for fun, I don't know, let me run this one that uses, let me have this open here, that uses wedge elements. So these are prisms, prismatic elements that you can kind of see here. Linear elasticity is probably, is we're solving for displacements, and in you can kind of visualize these displacements in GLVis like this. So this is the this here is the initial configuration, and this is the final configuration. And the vector field that we're solving for, the inverted minus of that vector field is what's shown here. And you have different ways of visualizing the vector field in GLVis. Okay, so this is linear elasticity. If you look at that example code, you will see that you can specify the Lamé coefficients, for example, and the bilinear form for that is called elasticity integrator, and it has the lambda and mu, the Lamé coefficients, as components. In this case, they're piecewise constant, so there is one material here and a different material here. So this is an example of a piecewise constant. Here's the schematics of what this beam look like. Okay, this is example 2. Please interrupt here. Please somebody let me know that I need to explain more. Example 3 is definite Maxwell in second order form. So this is something that appears in electromagnetic diffusion, time domain methods. It's a challenging problem because you have a curl operator and curl of gradient is 0, so you have a large neo-null space. And there are specialized algebraic multigrid methods, some of which we have developed to handle this problem well at large scales. So let me maybe do this run. Okay, wrong place. Make sure that you click on the terminal when you paste. Okay. Ooh. Okay. I had the solution here is also vector field, but it's not a displacement, and I had the displacement on, so that's why the mesh looked funny like that. So with analytic elements, they have scalar degrees of freedom that correspond to vector values, and this is the solution for this particular problem. It's a simple test problem with no solution. Let me just highlight a few things in the code here, for example, 3p. So the integrators here are this curl-curl integrator that corresponds to this term in a weak form. When we integrate by parts, you get curl-curl. And the vector finite element mass integrator, which is just this guy. This corresponds to identity, but when you in a weak form, it's an integral that's UV, that's called mass. And Nedelec is an example of a vector finite element in MFEM, which is, again, something that has degrees of freedom that associate with scalar quantities, but our result is vector, as opposed to having the vector as a Cartesian product of scalar spaces. And that's what this second integrator is. And you can see here that an example where you can just add integrators to a bilinear form and you automatically get the sum. That's what's the assumption. If you have a vector solution, how do you toggle in GLVis to the different components? If you have a vector solution, first of all, if you press V, you get different views of this vector field, either the exact vector field or the vector field scaled by its magnitude or colored by the magnitude. In 3D, you also have F, and what I will remove this vector field now, which shows the X, Y, and Z component or the magnitude. So it's capital F to show the individual scalar components. The arrows, the vectors is V, and it has 4 modes. And for elasticity, you also have this option to use the vector field as a displacement or not. And that's B and N. As I said, you can consult that. Here's the vector field, and here's the F that I mentioned, and the displacement is B and N. Okay. All right, so that's example 3. Example 4 is similar, but for HDiv. So this is a grad div problem, not to be confused with the div grad problem, which is Poisson. And so again, this is for example, for fluxes that naturally, they, for example, naturally have a continuous normal component. Otherwise, it's a very similar problem to this one. It also has a very large near-null space because the divergence of curl is 0. And so it needs specialized solvers, and we've actually spent a lot of time on this problem. If you go to the solvers lesson, you will see some links to papers, including some quite recent ones. I will just run maybe this one to show an example where the input mesh has adaptive mesh refinement in it. That is one of the things that MFEM is really good at. Adaptive mesh refinement, both conforming and non-conforming. And here you can kind of see, this is a simple example, of course, and just a test problem, but here you can see that we've refined the center, and let me just turn off the vector. This is, the solution here is also a vector one. We have refined the center, but the solution is still continuous, and you can see different. Sorry, the solution is still continuous in the still conforming in HDiv, and you can use this does not have the latest and greatest actually vector field visualization, but can kind of see the vector field. I can do it. Maybe this is better. Pick a different at this one. Can kind of see the HD vector field here. Okay. All right. That was example 4. Example 4P. Now, so far we've covered the first 3 rows in the the first 3 columns in the RAM complex. The last one, maybe the most natural choice is discontinuous Galerkin. So MFEM also supports general discontinuous Galerkin methods. In those methods, the solution is discontinuous between elements, but you add phase terms with specific jumps to still enforce that you're approximating the continuous solution well. And DG is particularly good for advection problem, for transport. That's what example 9 is. To transport. And let me show, maybe this is an interesting one. This is a time-dependent problem. So this is new. Oh, I have not built example 9, so let me do that now. And let me also build the parallel version. By the way, you can just say, you can just build all the examples, and this way you don't need to worry about doing this. Okay, maybe I could have, I put dash J4, but maybe I could have put even more. We do have quite a bit of examples. Maybe this was not a great idea. Okay, done. All right, so let me run the example 9 again. This one, yeah. Okay. Okay, now you can see here that it says GLVis visualization paused, press space to resume it. So what has happened now is we're computing solutions in different time steps, and we keep sending them, and they will kind of be shown one after the other. So space is one option. There is also this, if you kind of move up in the window, you will see this pause button here. So if I click it, you will start seeing how this problem evolves. In this case, it's a vection where the velocity is kind of swirling. And you can kind of see the solution and the mesh as it evolves in different time steps, approximating the solution of this equation. As you can probably guess, it's going towards something like this. And this is done with, even though it's not totally obvious, these elements actually are discontinuous. And I will pause to show you that they are in a second. But in the meantime, we can just, this is kind of one of the cooler, you can kind of see it in the light. This light is not very smooth. Okay. And I'm gonna actually stop this here, and I'll kill this and hope that this is okay. And let me just make sure that everything has arrived. Okay. All right, so let me refine a little bit the visualization. Okay, so now the visualization is refined. Maybe I should have let it run a little bit more. It's still not very easy to see discontinuities between the elements here. But they are discontinuous, believe me. Even though at this level, it can, yeah, okay, I can kind of see something here. I don't know if you guys can see it. Right here, these are some values that are not, there's some white here. So this is not, or also here. Anyway, so that's DG. We support this continuous gluerkin too. And there are a number of other runs that you can do. And anytime you have a time-dependent simulation, make sure that you wait for all of it to go through. Otherwise, the pipe between those two browser windows can get clogged and we need to restart. If that's the case, let me tell you what to do. If your GLVis window stops responding or it's out of sync, go at the bottom of the finite element basics where it's GLVis interface. And there's this command here. You need to kill the browser server in this window with this command, and then you need to reconnect from here if you're having issues like that. Okay, so I was in the examples. Okay, we did example 9. Example 10 is a nonlinear version of elasticity. And this is this new Hookean model. This example, we need to change it a little bit because it's opening 2 visualization windows, and this web demo is only currently supporting one. It's this main one. So we need to disable the second one. And you can do that by just going to example 10 and search for vishost, for example. Okay, and as you can see, there are kind of 2 visualizations. There's one for V and one for W, and the suggestion is to just disable the W one here, like this. Okay, so you will need to remake the example with that change. Okay. And if you want, you can do the same also here, in example 10p, the file version. Okay. Oops, sorry about this. All right, so let's see. Yeah, let's try this one. Okay, so this example actually has number of different ways to solve this time-dependent problem. Some are implicit, some are explicit. Um, this default one is an implicit Newton solve here, and let me see. You need to press space again because this is a time-dependent problem. So you're seeing the evolution in time, and this one takes in serial a while, as you can see, and you will only get the updates occasionally when you add these steps. So this is not continuous. Now I will stop it here. Again, hope everything just worked. And let me try to do the parallel version of it. Maybe I can even do 8 here. Let's see if that's okay. And as you can see, this goes a bit faster. I run on 8 different ranks, so you can see I pull them apart with F11. You can see them being computed. There is all the displacements that are computed here with V. The other window that we disabled shows the elastic energy, so you can look at them at the same time. So I know somebody asked about nonlinear elasticity here in the chat. This is the right example for that, and it's one of the basic examples. Okay, I mentioned adaptive mesh refinement. That is one of our hallmarks. Let me maybe do this one, but I want to do it in parallel. So let me do, I don't know, 8 processors. Let's see what will happen. Oh, here we go. All right. So the best way to look at this is from above and on a color map that's kind of white. So I'm gonna, yeah, I like this one, and I put anti-aliasing. All right. So what happens here is we have these rings, and we refine and de-refine at the same time the mesh to resolve the rings. And basically you want big elements in the interior and outside, and you want small elements near the boundaries of the rings, and they grow. This is not an actual physics problem. This is prescribed solution that evolves in time, and we're just testing this adaptive mesh refinement capabilities. They start intersecting, as you can see here. And they form these interesting patterns where they force us to make non-obvious decisions, well, visually obvious, but non-obvious from a code perspective, where to refine and derefine. This example 15, and I will pause it now. You can see this this loop going on here. I will close it now. Just to show you kind of what the solution actually looks like at this point and how we've refined and derefined. And again, I run in parallel. So F12 again. This should be with command. And you can see the different pieces. When we have a non-conforming adaptively refined mesh like this, non-conforming is refers to the fact that we have, for example, nodes like this one here, where there's a refinement on one side but not the other, or like here, where it's two refinements, so 4 elements on the left and only one on the right. And we need to constrain the degrees of freedom on the find side based on values on the core side. So when we have a mesh like this, we use a space filling curve to actually partition the MPI ranks. And you can kind of see it, it's called a Hilbert curve, to have almost the same number of degrees of freedom, the same number of elements, and then correspondingly degrees of freedom. And that's what happens here in parallel. Okay, so come back. Okay, there's also complex valued problems. The way we handle complex problems is via 2x2 real reformulation, where you have a real and imaginary part. That's kind of, there's no direct complex arithmetic, but you get the same solution and you can precondition it. And example 22 actually does kind of H1, H-curl, and H-tip versions of that. I'm not going to run these two, but you can kind of see and look at it if you're interested. Same for PML. That's a perfectly matched layer absorbing boundary conditions. There's example 25. They require some changes that are to be run in this environment that are pretty straightforward. Okay, so I see that we spent about 25 minutes on this example, on this lesson. I want to go for some of the others. So let me pause here and ask, and I know I went quickly, but any questions on any of these examples so far? Okay, I see quite a bit of discussion on Slack and in the WebEx chat. Anything I should address, guys?
Sonia Wan's asking
Is load balancing done every time?
Yes.
No, it's up to you when to do the load balancing. You initiate it. Okay, anything else? This is just a small selection of the examples. If you go to the end, or if you go to the examples page, you will see much more. So it's just fm.org/examples. All right, let's see. Meshing and visualization. Let me go very quick for this one. Basically, this was asked earlier, and I mentioned it. We support input from all sorts of mesh generators, Gmesh, Qubit, NetGen, and others. And it is fairly straightforward to add a new one. I think pointwise, for example, added some. This here is an example. In this lesson, it's about how to define a GMesh mesh. Then say, this is the corresponding geometry file, and then this results into some actual mesh output from GMesh, this MSH file, that then you can use in MFEM. And actually what happens here is we show you how to drop it inside this environment. So let me actually, okay, I have this file, so let me see if I can just do that. So you can, if you have a mesh file, you could in principle just drop it here. Just drag and drop it in the Visual Studio on the right, okay? Okay, so now I have it. And now this means I can just run it, use it as one of the meshes in my, oops, here. In my simulation runs here, but I need to put oversubscribe for this particular run. Okay, let's see what will happen. Okay. Right. Oh, this has this no vis at the end, which disables the visualization. Let me actually. Oops. For some reason, this shows only the interior boundaries. It doesn't show all the boundaries for some reason. Okay, I am not sure why this. I think the solution is correct, but it shows it does not have all the boundaries in the mesh. If you cut the solution, you can see that it's correct, but the mesh does not include some of the boundaries. Interesting. Maybe that's why I had noticed. Okay, but in principle, you could just drop any mesh. And then the other thing I think that this shows is a little bit further down is that you can then actually get results that were generated. So in this case, with I think this produces well, it could this hasn't been enabled, but it could produce a part of your output that then you can create a tarball of, download it locally, and look at it with PowerView yourself. And that's what the example actually is. So in PowerView, I guess this other boundary faces are just shown. There's another portion here that I want to say that I want to real quickly talk about, which is the meshing tools inside MFEM. And they can be, there are a variety of them. Some of them generate meshes. Some of them, like this Mesh Explorer tool, are tools for exploring, understanding, playing with meshes. Seeing, for example, if they have inverted elements or adding a random perturbation to them. They're in this miniapps directory. So including, in addition to examples, if you go one up and then you go to miniapps, you will see that we have a number of more advanced, they're not examples anymore. We call them miniapps because they may include a little bit of physics, or the code is just more complicated, okay, very specific tasks that they're trying to demonstrate. Is meshing, and let me build everything in meshing. And one of those examples in miniapps meshing is Mesh Explorer. So Mesh Explorer, let me see what is the example here. I don't know, we can take any of the example meshes and it's 2 levels up now. Let's say star Q3 maybe. Just for fun, star Q3 mesh. All right, and what you get then is you get this menu that tells you you can refine, you can change the curvature, you can make, for example, a mesh that is not curved, and you can view what's going on. So this is the default. This is what this star Q3 mesh looks like. It's a third order mesh. But let's say I change the curvature to 1. And now what I've done basically is I projected the cubic function to first order, and now this mesh is it becomes straight. I can look at element sizes, which for this mesh are almost the same. But this could be very useful when you have elements of different orders. You can look at scaled Jacobian, you can plot the function, all sorts of things. So I'm not pressing, as you can see, they're almost the same. Can use it also to generate a partitioning, which means to split this mesh for parallel computation. And there are a variety of methods that we support for that. And this is kind of to test how things will look like. And again, I need to be in this window. This is splitting it in 3. So that's one useful meshing tool. Then there's this shaper one that resolves interfaces between different materials or generally a function and different values of this function. So this could be used to generate meshes, for example. We have a kind of companion miniapp to that called Mondrian, where you can put any picture, for example, and it will try to resolve the interfaces between different colors. So try to get you something where each color is on domain. And this is the default shaper resolves this kind of annulus. And it's an example of non-conforming gamma. Okay. All right. Yeah, and yeah, Mandel is for the Mandelbrot set, but Mondrian is, you can basically, if you have a picture of it, you can create a mesh that you can compute on, and each color, cluster of colors will have the same element attributes or the same material. Okay. I will stop here for this page. Any questions on this one or any of the previous one for that matter? Okay. Then let me try to also talk briefly about solvers and scalability. This is where we do a lot of research, and in general, MFEM is kind of a delivery vehicle for the research we do in CASC and at LML, and solvers and large-scale scalability are a particular focus for us. I did mention already that we are very integrated with Hyper, the scalable linear solvers library. And so these 4 examples, kind of prototypical scalar, H1, vector, H1, H-curl, and H-diff, second order definite problems, we have Hyper solvers for each of them that are very performant. For H1, that's Boomerang G. And what's in this lesson is additional parameters and optimizations and talking about things like weak scaling that you can do in the example with the Boomerang G solver to actually have this run at very large scales in parallel. This is kind of the building foundation of everything. It's relatively standard. For linear elasticity, we have both what's called a system version of MG for system, and we have a special solver. Special MG solver is based on actually a paper that we published on this more than 10 years ago. That's enabled with this elast option. So if you don't provide the elast option, you get the regular solver and the regular MG for system solver, that is. And otherwise, you get the specialized elasticity solver. Sometimes this could be helpful. So if you do use elasticity, I would encourage you to try this. It's not always helpful, unfortunately, but sometimes it could be. And there are some example runs for that too. If you are interested in hcurl and hdiff, for hcurl, we have the MS solver that has been in hyper for a while, and that's an efficient MG style preconditioner for this problem that can really solve them quite well. For hdiff, we have the ADS solver, which is in the same family as AMS. It basically reduces the problem from hdiff to hcurl and h2h1, and that h1 problem is handled with MG. It is an efficient. It is a effective solver, but it's not very efficient. It solves the problem with work that's kind of independent of the problem size, but that work is a lot. We have a better way of solving hdiff problem based on hybridization. That's again a paper we wrote on that. And actually, this is not here, but we have an even newer work on a kind of saddle point formulation for hdiff that is particularly good for GPUs. So this, we have at least 3 different ways to solve hdiff, and all of them could be good, but this new saddle point solver is really, really good. And this is the latest we have. Okay. So these are kind of the standard AMG solvers. We also have native multigrid solver, example 26, showcases that. And in particular, we would like, when we do high order methods, not to assemble the matrix. So this is this idea of partial assembly and using the finite element decomposition in MFEM. That's very central for a lot of the research methods, the high performance computing algorithms, exascale supercomputing related algorithms, where, as I said, instead of having a global matrix A, you have these components, the PG, B, and D matrices that give you the transfer from different set of degrees of freedom, global degrees of freedom to degrees of freedom on the MPI rank, to degrees of freedom on each element, and then to values at quadrature points. And in the partial assembly case, you only assemble and store, you only compute and store D, and everything else, the B, the G, the P, you have them, but you don't multiply them, and you kind of, and even B, the action of B may be applied indirectly through what's called sum factorization when the elements and the quadrature points have tensor product structure. Okay, related to that is this family of low-order refined methods, and that's an idea where you have a high-order discretization on how the mesh, and you precondition it with first-order, low-order discretization on a refined version of the mesh. So it's kind of, you can see this macro element here, small low-order elements, is derived from this higher-order element. This has been a major research effort for us that has produced this low-order refined methods that are extremely efficient. They allow us to be still matrix-free and only partially assemble hard operators, but precondition them efficiently by assembling a sparse version of these operators, these low-order refined ones. And this is exemplified in this solvers set of miniapps. It's one level up from the meshing. And in particular, for example, the P solver, the PLOR solvers, the parallel LOR solvers version. And let me just do one run with that. So this was this is 260,000 degrees of freedom, order 5, and this has no visualization. That's why we don't see anything. And as you saw, that went really fast in 2D, and this is in 3D second order, more than 2 million degrees of freedom. Oversubscribe. I consistently misspell this. And it takes a while to get going here. Keep in mind, we really only have 8 actual cores here, so maybe this is a bit much. But the total problem size is quite significant, and this is 3D. Okay, while we're waiting here, any questions? I know I'm going very fast, so I hope you guys are following or doing your independent thing. Any questions on this? Or anything I showed so far? There are more details. These are more the kind of cutting edge of research. There's more details in some of the presentation. This is Will's presentation from the MFEM workshop, and this we record these talks, so you can also watch the video. Okay, and as you can see, even on this cloud machine, this is working. You can solve second order problems in 3D in a reasonable time. Okay, there are other solvers and integrations, Petsy, SuperLUs, Trumpack, Ginkgo, NGX. Some of those got mentioned. MFEM has a lot of optional integrations with a lot of other numerical methods libraries that are very easy and straightforward to use. For a lot of them, we have even independent subdirectories where they're highlighting this integration, specifically highlighting it. And you can diff the version of example 1, for example, in the Petsy directory with the main one to see the changes that you need to make. All right. So I did cover all 3 of them, but kind of fast. And I will encourage you, if any of those is of interest to you, a particular portion of it is to go back if you can and look at it later. And of course, you can come back and ask us questions. Okay, we have 15 minutes left, so I will go to the last page here. And just say that there is much more to do. If this has piqued your interest, there are many more examples. we've highlighted here with stars, the ones that might be worth checking. And they're kind of briefly summarized. There's these integrations. Most of those have serial and parallel versions, so that's another thing to look at. I did not talk really that much about the mini apps. I basically mentioned Mesh Explorer a little bit and maybe Shaper, but we have much more. Particularly, we have quite a bit of electromagnetic mini apps, static, dual heating. That's a particular strength of MFEM electromagnetics. We also have incompressible flow mini app Navier. It's also very performant and follows a lot of the methods in codes like NEC 5000. We have a capability for general interpolation in physical space and being able to have Schwartz coupling between overlapping grids. We call this GSLib. There's several examples of this. Distance solvers and kind of shifted methods. That's another capability that we have that is very useful. And then there's discontinuous Petrov arcing and the submesh extraction that allows you to take meshes that are portions of the domain or portions of the boundary and be able to transfer data between them and the parents to have interface coupling and to have multiphysics coupling. And this is just really a portion of it. Then there are separate mini apps like Lagos and Ramos that are outside of the MFEM repository and are designed to be particular mini apps for applications of interest, in this case, Livermore, to some compressible flow simulations we do inside the lab. And these are used to work with vendors, for example, when we are procuring new supercomputers. And then there's these toys. I mentioned some of them. For example, the Mandel mini app is Mandelbrot set. You can run it on the client bubble if you want. Why not? Let me do this just to show you. And you should be able to just do this, copy and paste here. Yeah, you can kind of see the Mandelbrot set taking taking shape on this client bubble. Okay. We would like, of course, for you to do your own thing, and would like to see your creativity. If you do something interesting, or maybe you've done something interesting already, we'd love to feature it on our gallery. We have a lot of interesting simulations there, and during our workshops, we have these visualization contests that actually one is coming up now, and people submit cool things they've done and get an award. You get a T-shirt, and you get the glory of being on the webpage and being listed as one of the winners. We do actually highlight the winners also here on the main page. So this is from the last time, the two winners. We typically end up having one award for videos and one for static images. Okay, this was all basically doing a simple developer environment with a simple GLVis setup in the browser. It is convenient and simple to use. But if you want, you can, of course, install MFEM yourself on your own machine. We have building instructions here. It should be pretty straightforward. In serial, it's really straightforward. There's no dependencies. In parallel, you have to build, you need to have MPI, and you need to build Hyper first. You could do all of this with SPAC if you use SPAC, and you can just say SPAC install MFEM and GLVis if you want. There are many things we didn't talk about, we touched on, in particular partial assembly and the operator decomposition, advanced GPU support, all these integrations. And there's also a wrapper that we have for Python called PyMFEM, and you can use it through Jupyter notebooks. That includes a version of GLVis, and you should be hopefully able to just click on this collab link and have it work. Let's see how long it will take. It takes a while to kind of get this set up, but after that it should be pretty fast. Okay, so this is done. And if you look at this example and this code, this Python code, this looks very, very close to actually the C++ code. You see all the linear forms and get essential true-offs and grid function. And you can just execute it. It tells you size of the linear system. And you can use this GLVis command. And now what you have here is basically the same as here. It's actually the same source. You can press the same keys, M, for example, and P to change the colors, and C and A and all of this. And so this is the solution, and this is if you want the mesh. And this is some of the keys being pressed. You can reproduce this here if you just press those same keys. So there's a way we support to kind of adjust the view. Okay, so that's also a possibility. More information, going to the MFEM website, of course. There's a lot there. There's the features that we covered already, but you can take a closer look. The example page that I mentioned. If you are interested in more the research side and the publications, we try to keep these up to date. And on the documentation, there's also these pages with finite elements, which we referred to several times. We record videos from both our internal seminar, our external seminar. This is actually a seminar for everyone at the lab, but generally for the MFEM community, FEM If you're interested in this seminar, under community here, you can sign up. But we have the videos from the seminar and from the MFEM workshops. And all of this are available on YouTube, and you should be able to watch them. There's a lot of really good material there. Okay, speaking of the workshop, that is coming up October 22nd to 24th. If you're interested, please join us. You can learn more at mfem.org/workshop. There's a registration, and you can join us in person at Livermore. You need to register by October 15th. There's this form here. Or if you're joining us remotely, there is no registration fee for that. But we would like you to register because just like for this tutorial, we're going to start sending specific emails to folks that have expressed interest to register. And it should be a cool event. It's really an opportunity to learn more about MFEM. We will have some office hours and breakout sessions on the last day with some hackathon, and we'll get more in depth, more on the cutting edge of MFEM's capability discussions. Okay, if this sounds interesting to you, you're more than welcome to join the MFEM community on GitHub. We have an MFEM organization, and inside the MFEM organization, there is the main MFEM repository. That's where we do all our development. There's a lot of people. Let me just point out more than 145 people have contributed already to the code, many of them now at Livermore. And in the community, we have something like 680 people. Plus, we're very open to contributions. We have rigorous quality control, of course, but you can read about the contributing guidelines in this contributing MD document we have. And if you like MFEM, if you think we're doing a good job, we'll appreciate you giving us a star here on GitHub. That actually is helping us with some of our sponsors. And if you haven't done so already, please consider doing that. Okay, final thing, if you want to get a hold of us after this workshop, the Slack channel is a possibility, but really the best way is to just use the GitHub issue tracker. And we try to respond there, but this is the official way to get a hold of us, and particularly the community, because it's not just the people at Livermore, there are a lot of other people that can answer, and you'll just get a quicker response this way. There's also a web address that you can, an email address that you can send email to, mfmdev@lnl.gov. But these days, that doesn't seem to be an actual preferred communication channel. The best thing, of course, is to just come to the MFEM workshop. That's the highest bandwidth communication that you can get. All right, that's, I think we're kind of at the end of time, so I'm going to stop here. I think that's everything I wanted to show and mention. Please let me know if there are questions.